Today we're very honored to invite Professor Raymundo Arroyave from Department of Material Science Engineering at Texas A&M to give us an exciting introduction of his current research in AI-enabled material discovery and design. Before that, I'd like to introduce you Dr. Raymundo Arroyave, and he is obtained his master PhD degree from MIT, and he's now currently a full professor in Department of Material Science Engineering, and he's also President Impact Fellow of Texas A&M. He has also received many distinguished awards. Among those, for example, the NSF Career Award, and he selected Young Faculty Fellow, and also the many distinguished service awards such as TMS EMP MD Distinguished Service Award, and which I'm not going to enumerate the rest. And his research has been focused on primarily in computational material science, and he's an expert in this area, especially in the computational thermodynamics, kinetics of materials, and working on many materials, truly wide range, from alloys to steels to functional materials and thin films, a lot of those, which is very exciting. And he's also performed a wide range of material-related research related to the physics of materials, phase stability, and computational aided materials design and materials genomics. So without further introducing additional background, now let's welcome Dr. Raymundo Arroyave to give us the lecture on AI-enabled materials discovery and design.
Thank you, Stefan. Can you see my pointer here?
Very clearly. I can see the pointer.
I don't know. Oh, I'm gonna put
right
highlighter. Whatever. No.
No. Actually, right click. I think is pointer and then laser color. Red.
Oh, laser pointer.
Laser pointer. Yeah.
Like this. Okay, cool. Yeah. So thank you, Stefan, for a very kind introduction. I'm gonna get started. First of all, I would like to congratulate all of the O-REU students. I have been watching several of the videos. I have watched 10 already, and I must say that I'm extremely impressed because I usually in typical REU program projects or programs, you don't see a very large fraction of projects carried to completion, and here I was happy to see that all the students completed their projects and they showed very exciting research. So I'm really happy. I'm very impressed by the timing. Students are way better at timing their presentations than professors. So I hope that I don't go over time, and I have a timer myself to tell me when to shut up. So hopefully this goes fine. Today I'm going to talk about AI-enabled material discovery and design. I will present some of our work, but I'm mostly going to focus on the history of materials design and materials development and the future. Okay, and in the middle of my talk, I will have some brief presentation of some of the stuff that we have been doing in collaboration with other faculty at Texas A&M. So we're going to start from the beginning, and if we look at the different approaches to materials development in prehistory, material development was mostly accidental, right? So people discovered the wheel, and by wheel I mean any interesting technology millions of times or thousands of times, because population density was very low and life expectancy was extremely low. There was very little civilization memory. So that means that whatever some genius a million years ago discovered, it was probably forgotten after his grandkids died or even his kids, right? So there was not a lot of accumulation of knowledge, and the discoveries was materials were discovered, and it was probably mostly by accident, right? Although humans have been clever all the time, and even there is evidence, for example, in prehistory, that people were heat treating rocks to make them tougher, less prone to fracture. So again, probably people didn't know exactly what it was, what they were doing, but they were learning how to modify, maybe not the chemistry of the material because the rock didn't change the chemistry, but they were changing somehow the microstructure by subjecting these rocks, for example, to heat treatment, right? So that's the way materials were discovered, and deployed in prehistory. At the beginning of our civilization, when we started writing histories and writing, and storing our knowledge in books and in monuments and in, script, in rocks and paper, etc., people were starting to develop rules and recipes that were based on empirical observation. And a very nice example of this, I don't know if you have watched videos or documentaries on this, the master Japanese swordsmiths that produce some of the best, or probably the best, swords in the world. They follow a recipe and a procedure that has been followed for hundreds of years, and they follow exactly the same procedure. They even sing, and pray, and do it at a particular time of the day, because of course that is very important to them. But also the singing and the praying and doing it, always at the same time of the day in the same way, keeps the process going in a very controlled way. So people discover some, complicated recipes to making materials, and without knowing exactly how, or why, the materials were behaving the way they did, people kind of said, well, I might as well follow this recipe to the letter without understanding why. This is, for example, analogous to the way we cook or we bake cakes or pies, etc. So we follow a recipe, and as long as that recipe works, we keep doing it. We may innovate here and there by trying some, adding a little bit of sugar, a little bit of, salt or pepper, etc. But we usually, follow the recipe without much insight on why we are actually doing that. In the modern age, particularly after, the Industrial Revolution, when we discover the scientific method, knowledge is organized and systematized, and the scientific method, based on experimentation, observation, hypothesis building, and hypothesis testing, contributes to a much better understanding of why materials behave the way they do, and this gives people some insight on what to do to improve materials behavior, right? So this is probably modern age all the way until, I will be I'm probably too old now, but all the way until my early years in grad school, this is the way people did material science and design materials, mostly. Now, if you look at some of the biggest problems or challenges for that can be associated with engineering, it turns out that about half of the grand challenges that have been already identified by the National Academy of Engineering require significant material advances, right? So from making solar energy economical, provide energy from fusion, which is an extremely difficult technological problem. I don't know if we're going to be able to solve it ever, but if we solve it, it's going to be because we discover some ways of engineering materials in a very special way. And like those examples, there are many other examples in the grand challenges that involve the development of materials. The problem, however, is that the material development cycle tends to be too slow, right? This is just a graph that I took from Professor Garcider, formerly at MIT, now at Berkeley. And in this graph, he shows, for example, the lag time between discovery and deployment, right? So you can see that, usually from discovery to deployment, the work that is done in the labs, for example, of many of your, O-REU advisors, to the point where that technology is sold into a market or deployed, in an application, it takes decades, right? 20 years or more for Teflon, titanium, also you can think of all kinds of structural materials, hard materials, polymers, etc., right? So it takes a long time to develop these materials, right? And, development cycle is slow because usually we discover materials, but we end up, concluding that they don't have the right properties. So we have to do a lot of iteration, trial and error, experimentation, and that just takes too long. Now, the problem that we have is that societal, economic, and environmental problems grow much faster than the current pace of technology development, right? It's really scary. I kind of avoid reading. I shouldn't avoid it. We should face it, but I kind of avoid reading news about global warming and how the Arctic, is melting, because every year things get worse, right? And they were getting worse in an at an extremely rapid pace, right? So the rate at which the problems are becoming worse is much faster than the rate at which we can discover new battery technologies, for example, that can store much more energy than the state-of-the-art lithium-ion batteries, or they move faster than the rate at which we can discover materials that can withstand higher temperatures, so we can enable more efficient, gas turbines for power generation or air transportation, etc. Right? So in many cases, the technologies are there. Engineers think through ways of solving these hard problems, but we don't have materials, right? So materials are technology enablers, but they are also technology killers if they are not there, if they're not available to do cool stuff. Okay, so 10 years ago, it was very exciting to learn that the U.S. government and the same thing was happening across the board in Europe and China and Japan. Came up with something called the Material Genome Initiative, and this there was a very famous report written in 2011, and actually in doing a parenthesis in the O-REU program, for this year, a lot of the work has been done on computational material science and data science applied to material science, mostly. So in a way, this O-REU is actually fulfilling some of the expectations of the Material Genome Initiative set, 9 years ago, right? So the whole point of the MGI was to combine computational tools, experiments, as well as data science to try to accelerate the way materials are developed. So here in this schematic, this is usually the time frame to discover a material or develop it, 20 years or so. The expectation with the MGI was that by combining these tools, it may have been possible, or it may be possible to actually shorten this, potential time to development to at least half of the time or even more. Okay, so the problem here is, how do you approach this problem, right? Going back to this slide that I showed before, I said that until recently, even the early age, like the early years of my PhD career, this is the way we did material science mostly, right? Um, but now we actually do it differently, right? We are doing, particularly when we are interested in discovering new materials and designing new materials, we are now trying to integrate four kinds of exploration. We are now becoming way better at combining experiments, theory, computation. Professor Chao-Feng Shang is an expert, one of the experts in the world in advanced methods for density functional theory and its extensions. And we have many people, advisors to the O-REU students, who are computational material scientists. And the idea here is, today, if we want to do material science, we actually have to combine theory, experiments, computations, and data. And by data, I mean data science, machine learning, etc. Okay, so why data science? Okay, so the MGI came up with this idea. It was at the time where big data was becoming a thing throughout, the human experience. It was when Netflix was starting to recommend movies based on the movies that you liked or you didn't like, and so on. So machine learning was all pervasive. Data science was all pervasive in all kinds of fields. And then, but the question here is, why data science and machine learning in materials? Well, one of the explanations, and there are many reasons why you would like to do this. One explanation is that one reason why machine learning would be useful in the context of material science is because humans are good at identifying trends in maybe 1D, 2D, and maybe 3D spaces, but material science problems have many more dimensions or factors, right? I mean, you have to worry about chemistry, you have to worry about processing, and processing can be defined in many different ways, right? So you probably have an almost infinite dimensional space with many things that you can do to, the 92 atoms or 92 elements, natural elements that appear in the periodic table to create useful materials to enable transformative technologies. But the truth of the matter is that humans tend to be really poor at understanding multidimensional spaces. It turns out that computers are much better at trying to uncover the most dominant dimensions in a multidimensional problem, right? So here I have an example of the application, and many of you have done that of principal component analysis to reduce the effective dimensions of a multidimensional problem. Sometimes humans are too good at identifying trends, right? So our uncanny ability to recognize patterns may lead us astray. So we may actually have some experiments in some region of the experimental space, and we see some trend, and we may believe that that is a trend that is going to hold forever, and we keep exploring in that direction. Maybe using machine learning, you can get some insights into whether there's truly the pattern that you are thinking of exploiting or not. And finally, and by the way, this is not an exhaustive, list of reasons why machine learning may be useful. Humans, we are not that good at looking for hidden correlations, right? So you may have multiple factors that are correlated with a particular property that we're interested in, and our brain is really good at recognizing patterns and trying to understand and manipulate information and take actions based on that information. We're the most intelligent system in the universe as far as we know, but sometimes we cannot uncover these correlations unless we do a lot of experiments and we have a lot of experience, right? And machine learning can help us in that way to a certain extent. Now, there are basically two components. When we're trying to do material design in the context of this modern way of doing material science, there are two ways of looking at the problem. First, you have the forward problem, where we're trying to build this connection between process, structure, properties, and performance. And in this context, we may actually use informatics or machine learning or data science, however you want to call it, to establish these linkages, particularly if our experiments, our computations are limited. So maybe we can build these linkages partially, at least, using machine learning methods. And here are just some examples of things that can be done in the forward direction. But the problem when we're trying to look at material design is not only that of building insights in the forward sense of establishing these relationships between process, structure, properties, and performance. When we're actually trying to discover and design a material, we're actually trying to go in the inverse direction. So here, in the forward direction, we're thinking like scientists. We're trying to get to the bottom of things, right? And we go from the bottom up. When we are trying to design materials, we actually have to, talk about engineers or think like engineers, right? So we are engineering matter. We are modifying, adapting, transforming matter in order to achieve a particular performance objective that is related to a particular technological need, right? Okay, so we need to somehow, figure out what type of strategies we can use to try to, look at materials and modify them in order to fulfill this goal-oriented, search and optimization. Okay, so the defining factor when we're looking at the inverse problem is that we're trying to find as efficiently as we can make this process to be a solution to a technological problem or to a problem related to a particular target property or behavior that we are after. Okay. Now, I'm going to try to make a little bit of a distinction between machine learning and AI because, in the title I say that I'm going to talk about AI material discovery, and I have talked mostly about machine learning. I'm not an expert. I'm a practitioner of material science that knows a little bit about machine learning and AI, and I work with very smart people here at Texas A&M who are experts in machine learning and AI. And the little that I understand, and this may be wrong, and I'm not gonna go into deep learning because I'm not using deep learning neural networks in my research, or at least in the examples that I'm gonna give right now. Is that machine learning is essentially self-learning algorithms that learn models from data. So you have a data set, and many of you did that. You had a data set, you present it to an algorithm, and the algorithm finds patterns in the data, either classifies the data into different categories or builds some sort of regressor model that is capable of making predictions of the outcome of experiments that you haven't run yet. AI, on the other hand, is a system that is intelligent through rules, right? So the important thing here is that machine learning is based on building models from data, and AI is about systems that kind of like adapt, change, follow rules based on the information that they gather, right? Now, going back to the problem of goal-oriented material design, what we want to do is to actually traverse these, connections in the inverse way, okay? Because at the end of the day, material discovery has to be a goal-oriented, activity, right? So material discovery is about how you navigate the material space with a purpose, okay? Now, the problem with this is that navigating the material design space, and I'm gonna call, like, I love to use material design space in my papers, okay? So I look at the material space as a material design space. That means that it's subject to improvement and optimization if you are clever about how you navigate the space. This space is very large, right? Actually, I don't think that there is any system at all, and we are far, far away from achieving the following. We cannot just say, I want to fly from here to New York and I want to spend the less amount of fuel possible. I don't think, and actually, I'm almost sure, I'm 100% sure actually, that there is no framework that would automatically arrive at, carbon reinforced fiber composites, for example, right? Which are the type of material that are being used right now to build the fuselages of planes, right? So, ideally, a new AI-driven system for material discovery should be materials agnostic, but that is not the case. We usually, and by the way, we material scientists tend to be specialized, right? Some of us are metallurgists, some are ceramics, experts, some are polymer scientists, some deal with composites, some deal with functional materials. We don't have the expertise to deal with all kinds of materials at the same time, right? So first of all, the material space is very large. And second, the material space is multi-scale. So the material's behavior cannot be explained at all by just looking at one scale. If you want to understand a material, you have to understand everything that is happening to that material from atoms up, right? Maybe when you're dealing with nanomaterials or 2D materials, you can live by dealing with 1,000 atoms, and that's your material. But in most cases, materials are multi-scale systems in which many phenomena happen at different scales, and you have to be aware of them, right? So that makes it difficult, for the material design space to navigate. Now, there are some approaches to try to explore this material design space in an efficient way. And one approach that is very common is high throughput exploration using, computers or real experiments. And in this case, high throughput is about carrying out a lot of experiments, then analyze the results, maybe with machine learning. You filter them, you evaluate the results against your goals, and then you declare a success if you can find something that is interesting or that is better than what you had before. Now, while high throughput type work, which I call Edisonian, trial and error, is a valid way of exploring the material design space. The problem is that there are many bottlenecks, right? So at first, you may have to figure out how to make a material, how to make many materials at the same time. So, you may overcome the synthesis bottleneck to a certain extent. But then the problem is that once you make these materials, then you have to characterize them, right? And characterizing materials takes a lot more time than making the material. It's easier to mix things, in a vial or in a furnace or whatever, than to look than to look at the material in a microscope and quantify the structure and measure the defects that you may have and so on. Now, even if you can develop, and there are many groups that are working on high throughput characterization techniques, the analysis itself may be, quite difficult. For example, if you go now to one of the photon sources, the national photon sources where you shine, very powerful lasers or electron beams, etc., uh, uh, on a material, you may get data sets that are terabytes, big, right? So it takes a lot of time to analyze a data set that is terabytes, even with modern data analytic techniques, right? So that is a big bottleneck. And now that machines are becoming better at looking at materials, the data that we're gonna get is gonna get so big that unless we develop really advanced revolutionary machine learning AI techniques to make sense of the data, it's gonna be very expensive and very time consuming to do this analysis. Most importantly, the decision. Sorry, the decision, of what to do once you have the material cannot be parallelized. At the end of the day, there's gonna be a human that is gonna make a decision, and this human is gonna be your advisor, or is gonna be this, chief technology officer of a company, right? It could be anyone that is gonna have to make a decision on where to go next, given the data that you have right now, right? So the big picture here is that, high throughput Edisonian ways of trying to discover materials may not be efficient, right? Particularly because there are all these bottlenecks. And most importantly, in these open loop approaches, there is no prescription of what to do next once more knowledge is gained, right? So there is no sense of actually closing the loop and iterating over a solution that you may have. So, the type of work that involves, dealing with, AI-enabled material design is about having some initial data, building some sort of representation, computational representation, easy to evaluate representation of the material space that we're trying to explore. Selecting, most of the work, by the way, has been done doing sequential experimental design. You select one experiment at a time, although in my group, we are now doing some really cool stuff, or my students rather are doing some really cool stuff, doing parallel optimal experimental design, where you actually try many experiments at a time. But the conventional way of doing AI-enabled materials design is you select one experiment, you run the experiment, and then you keep iterating until you run out of resources, or you feel satisfied with what you have found. Now, I want to make a distinction here. A very famous AI expert from Oxford, whose name is Nando de Freitas, he's from Portugal, I believe, wrote a position piece, a couple of years ago, and they actually define autonomous systems as those that are able to build and exploit their own internal models and act on them, in order to fulfill a particular target, right, or objective. So this loop that I have given you here is not really autonomous unless, the model itself can change based on the data that you have, right? So it's not just about feeding a better model. It may be about, finding different models to try to fulfill the experiment or the goal, right? So usually AI enables material discovery, and there are a lot of people right now publishing papers on self-driven laboratories and so on. Essentially, what people are doing is Bayesian optimization, which is basically what I showed here in this loop. So if you hear AI-enabled material discovery, it's just a fancy word or phrase for Bayesian optimization. This is basically the state of the art. And Bayesian optimization consists of two things. First, you build a machine learning model or response surface model that is very easy to evaluate, that predicts the outcome of unobserved or or experiments that you have yet to carry out. Okay, and then you have an acquisition function or criterion, which is the policy or the rule that tells the algorithm what to do next, given the information that you have acquired yet. Okay, so I'm going to skip this because I'm running out of time, but I'm just going to show this example here. This is a Bayesian optimization algorithm in action. I have this, problem. I'm trying to find, this maximum. Here is a problem that has a lot of local maxima, and I'm trying to find this maximum. I have made these observations, 1, 2, 3, 4. I have a model, a machine learning model, and the model predicts the average outcome of experiments that I haven't run yet with uncertainty. And notice that the uncertainty is bigger the farther apart I am from known information, right? Here, so this is basically the model component of Bayesian optimization. And here I have, a plot of the utility or the acquisition function that I'm using to select what experiment to run next. So if I run this, I'm going to find here, for example, that at the beginning, the algorithm is telling me that I should explore at x equals 10. Then it's telling me that I have to explore at, x equals 9. And if I keep doing this over time, right, trying to figure out and follow the policy that maximizes this, utility that I plot at the bottom, eventually, over time, I get the answer that I want, right? So Bayesian optimization is just a fancy word for trying to optimize black box problems that are difficult to evaluate with the least number of tries possible. If I actually had tried to solve this problem using genetic algorithms or other type of optimization schemes, it would take me hundreds of more times or more iterations than the number of iterations that it took me in this case to find the solution. Okay, so going to the point that I wanted to show you some little examples that I have. We apply this type of Bayesian optimization scheme to try to discover a particular property that we were interested in the space of max faces. I don't know if any of you work with Professor Radovich in the O-REU, but Professor Radovich is an expert on max faces. These are essentially layered ternary carbides or nitrides. And there's a very rich chemistry. And the idea here was whether we could actually discover the best material by using this approach. So in this case, we actually tried to do something autonomous-like because we actually selected multiple theories for what type of features in the material space were important and were correlated with the experiments that we ran. And then what we did was we ran this Bayesian optimization. And what we discovered is that, sorry, the text doesn't appear here, but some features are actually effective, right? So if you pick feature set 2, you get to the answer in the right time. On the other hand, if you pick feature set 5, and when I say feature set, imagine that you have a model, you say, well, maybe the row in the periodic table and the atomic size and the number of valence electrons is important. And some other people may say, oh, no, actually is the column of the periodic table and the molecular weight and some other atomic function or property that is important, right? So if you're lucky enough to pick the right feature, you get to the answer in the number of tries that you have at your target. If you pick the wrong feature, you're not that lucky, you're not going to be able to achieve the target in the budget that you have. So what we did here, we use something called Bayesian model averaging, which is basically the technique that people use right now to predict the path of hurricanes, for example, when you have multiple models and you fuse them together. And what we did was to develop a system that actually figured out how to combine all these different models in a way that the system was robust against picking the wrong model, right? And if we want to look at how here I'm plotting the weight or the importance of the different models as a function of carrying out the experiment, we see that some feature sets are always important and become even more important at the end of the experimental campaign. Some feature sets the algorithm immediately detects, or at some point detects, that they're not important, and they lose importance completely, right? And some feature sets, for some reason, are not very important, they become important, and then the importance goes down again. So in a sense, in our case, in this system at least, we built some sort of framework that on its own selected the model that was best to use at any point in the experimental campaign, given the information that we had. Okay, so what is next, right? So there's a lot of work. One leader in the field is Professor Alan Aspuro-Gusick from the University of Toronto, and he has been writing papers here and there about self-driven laboratories. And in reality, self-driven laboratories is nothing more than and I think that I have a slide in a few minutes that shows this. But self-driven laboratories is just about how do you actually figure out a way to navigate a candidate space in a materials problem in such a way that you have a closed loop. So you let some sort of robotic system do the experimental selection for you. So self-driven labs are nothing more than a Bayesian optimization, what I showed just now, with an automated robotics platform, right? So if my algorithm were able to actually talk to an automated robotic lab and tell it, what to combine in which way, I would have a self-driven lab, right? So the self-driven, as long as you have an automated robotics platform, I mean, you're all set. The important thing here is what type of, algorithm you're actually using to select the experiments to run. Now, is this really autonomous? I mean, actually, the fanciest self-driven platforms, are, as I said before, is just a Bayesian optimizer that controls a dumb robot, right? So, we may actually have, question whether this is actually an autonomous system. Now, this is autonomous, right? This is science fiction. This is from Iron Man 2, and I just watched it over the weekend with my kids. And in this case, Jarvis, which is the AI of Tony Stark, not only discovers a material, it actually discovers a new element, right? And this new element helps Iron Man in some way that I still do not understand. Okay, we're not quite there yet. Okay, because there are many problems, right? So we have to recall that problem spaces in which AI thrives are usually low dimensional, right? And and material spaces tend to be multidimensional. Many conventional machine learning and AI approaches, imply strong assumptions regarding the smoothness, continuity, and non-singular nature of the problem space. So this is basically a model that is very smooth over the design space. The problem is that materials may not be smooth or continuous. Here, for example, I have the nickel aluminum binary system. Here I have a region of the space that is relevant if you want to build protective layers of these, turbine blades, for example, right? And this region is very different and behaves very differently from this region here, which is the one that you're interested in if you're trying to design microstructures for the blade itself, right? So clearly the space of design for bond codes, as these things are named, and the superalloy itself, which corresponds to this region, are not continuous, right? And typical machine learning models do not deal with these non-continuous problem spaces. Most importantly, material spaces may be singular. If you're actually trying to design a smart material or a functional material, you're looking most of the times after a phase transition, and phase transitions happen at a very precise region in the composition, temperature, pressure, magnetic field space, right? So this is like finding a needle in the haystack, and machine learning methods tend to generalize very well. But finding a phase transition is about finding a very specific behavior that may not have many examples in the entire material space that you're trying to explore, right? So potential paths forward, we may actually have to rethink machine learning and AI to develop new frameworks that are tailored specifically for material science. Another way forward is to insert more physics and chemistry into machine learning by building machine learning models that are constrained by physics rules, for example, or by chemistry rules, and also by working on the representation problem, which is basically how do you tailor the way you represent the model in order to better, relate it to material science. So I'm running out of, out of time. I apologize, for this. But in general, I think that there's a lot of work to be done, right? But there's a lot of promise in machine learning and AI-driven material science. And all of you who are interested in material science are arriving at the field at the right moment, because I think in the future in our field is extremely bright. With that, I would like to thank you for your attention.
Thank you, Raymundo, for this very exciting and nice introduction of this AI in material science. Any question from the audience? This is a really exciting opportunity for you to ask any questions related to AI-enabled material science.
I guess I ran, sorry, go ahead.
I have one quick question, by the way. Regarding this very hyperdimensional space, is there a way that we can come up with eventually human understandable or interpretable rules eventually learned from those hyperdimensional space? For example, going beyond 3-dimensional, maybe like say 5 or 6 or even 10-dimensional space in the parameter space.
So you can do dimensional reduction, and you may have some hope of making sense of the data. There's a lot of work, for example, on using neural networks to solve material science problems. But even the whole idea of understanding why a neural network works is still a state-of-the-art, a state-of-the-art challenge and problem in computer science and mathematics, right? So there are professors right now in the math department and computer science whose job is to try to understand how even the simplest neural networks work. It's still not understood, right? I mean, you run it, you train it somehow, and you get some result, but how can you make sense of that result is not that evident. And that is still a state-of-the-art problem in, foundational, computer science, right, and mathematics.
Right.
So that's still a problem to solve.
Right. I also feel excited to look forward to those progresses, because one fundamental question to me is that if there's such a like fantastic machine, is it possible eventually one day we can truly comprehend the logic that that we can understand at the human level, or maybe at a certain level we are probably not able to understand those very complicated models?
I mean, my feeling is that first we will have to, create a general AI. Once you create a general AI, it will become an expert material scientist in a second, right? Okay, an expert on anything, right? But you first have to generate a general AI, and that is going to be difficult. And by the way, even if you create like a super smart AI that is, much better than any material scientist, that AI still will have to run experiments. Right? And experiments, the time at which you can run an experiment is controlled by fundamental laws of physics that cannot be overruled by machine learning on AI. At the end, if you want to know, what is the behavior of a material after 1 year at 1,000 degrees Celsius, you have to wait 1 year, right? For the material to be in the oven and then get it out, right? So at the end of the day, even if you build a very smart AI, it's going to still be stuck with the laws of physics in this universe, right? So it will take time to run experiments. It will be expensive to run experiments, etc., right? It may be cheaper than now, but it will still be expensive, and it will definitely still take time, right? So, it's not going to be magical. We're still going to do experiments, for forever. And the question is just whether we can actually do this a bit more efficiently than the way we're doing it now.
Right. Yeah. Very, very, very exciting. I'm thrilled to see so so much progress in the field, and especially the recent rise of this AI system, right? The combined robotics and the one that introduced the whole right now the Bayesian optimization based system that integrate the hardware, like say our chemists, material scientists, computational material science like you and many other leading experts in the field in such a very tight and also closely collaborated manner. In the past, like both of us have been doing a lot of like a computational material science with experiment, but right now you're truly integrated the whole thing together, which is really cool.
Yeah, I agree.
Yeah. Any other questions from the O-REU students? I know this Friday will be your celebration day, but that means also it is going to end very soon. So take this chance to ask any questions.
And if not, you can email me. You can watch the video later, and and hopefully you have learned something new. Okay.
Great.
But good luck to everybody in your future endeavors. The next semester is probably going to be challenging for all of us because we do not know what is going to happen, and we do not know how we're going to take classes or give classes. But just be safe, and good luck on everything. And thank you for your attention.
Thank you, Ray. Okay. See you.
Thank you.